Dear colleagues, can you hear me?
Hi, Daniel.
Oh, yes, I can hear you, Ivan.
Hello, everybody. Good morning, good afternoon, good evening, good night. Welcome to our seminar. Today, we have a pleasure to have our speaker, Professor Daniel Nakano from University of Georgia, United States. Professor Nakano participated practically in all our conferences at LieJor and Algebras here in Brazil physically, and now he will participate virtually. He has very intriguing title of his talk, New Lie Theory for Classical Lie Superalgebras. I'm eager to listen to this. Well done. You can start, please.
Okay. Thank you, Ivan. Let me, first of all, switch to a full screen mode. So, view full screen. All right. Can everyone see the full screen? Yes?
Yes.
Okay, good. Thanks. All right. So I'd like to first thank the organizers for the invitation to speak in the seminar. Over the years, I've become even more appreciative of the efforts of Lee Jordan. I think it's really great how the Lee Jordan group at Sao Paulo has actually brought together the community, and it's a really vibrant atmosphere that they provided through their seminars and also through their conferences. All right, so let me move on. So I'd like to actually sort of talk about these two books. So when I was constructing this talk, I sort of thought about how I actually learned the basics of Lie theory. And these two books actually came to mind. And the first one is a classic. We still use this at the University of Georgia when we teach our graduate course on Lie algebras. And the second book, Conjugacy Classes, I'll actually reference a lot of the material from this book in my talk. So Jim Humphreys was a very important mathematician in the area of algebraic group representations. His books and expository articles were instrumental in the development of the field. For me, Jim was very supportive of younger mathematicians in representation theory. When I first entered the field, he actually wrote an extensive math review on my PhD thesis on projective modules over Lie algebras of Cartan type in 1990. I'm also very indebted for Jim's words of encouragement over the years, his careful reading of my work, and for his guidance during this time. Many people might know that Jim passed away due to COVID-19.
Oh, no.
August 27th, 2020. So, yes, so we really mourn his loss, and we mourn that we'll miss him quite a bit. Okay, so I'd like to first of all start my talk by sort of going back to sort of the basics. So a lot of this you can actually find in Jim's book. So we're going to start with the basics of Lie theory. So let's start with G being a complex simple algebraic group, script G being its Lie algebra. And if you want to classify simple Lie algebras over the complex numbers, we sort of know how to do this. You can take a maximal torus, and then what you want to do is find a root space decomposition. Now, in the process of finding the root space decomposition, you get a triangular decomposition where you have sort of the positive root vectors in n plus, and then the negative root vectors in n minus, and script t is a maximal torus. Okay. Now, whenever you take the root vectors, you get an irreducible root system. And you sort of axiomize the notion of a root system, and then you actually classify root systems, which are irreducible. And this actually classifies the simple complex Lie algebras. As we know, there are 4 infinite families, AN, BN, CN, and DN, and 5 exceptional families. Okay. Now, also, what's important in the game is the Weyl group which are reflections that arise from the root system. Okay, now in the process of classifying complex simple Lie algebras, one of the important ideas is the idea of the Jordan-Chevalier decomposition. So whenever you take an element of the Lie algebra, you can write it as a semi-simple element plus a nilpotent element, which actually commute. So, you know, if you just think of like GLN, for example, you can conjugate any X in terms of its Jordan canonical form. The XS consists of diagonal matrices with the eigenvalues, and the Xn consists of the sort of the nilpotent Jordan blocks. All right. Now, the XS corresponds to the semi-simple elements. The Xn corresponds to the nilpotent elements. And if you want to characterize the semi-simple elements in the Lie algebra, you can take a maximal torus, and then you could just hit it by the algebraic group. So we have the semi-simple elements. Now let's talk a little bit about the nilpotent elements. So whenever you have a nilpotent element, you can take the collection of them, and it turns out that this is an affine algebraic variety. And we'll see why in a moment why it's actually a variety. We know that you can sort of conjugate nilpotent matrices, and this carries over to the variety of nilpotent elements, sometimes called the nil cone. And so G will act on N via the adjoint representation. And a deeper fact is that for any complex semi-simple Lie algebra, the number of nilpotent orbits on N is finite. And you can actually classify all the nilpotent orbits. So like for GLN, you just look at the Jordan blocks. You can sort of order them by size, and then you get a partition. You get a correspondence with partitions of N. And so you have a partition type classification for like GLN. This carries over for the other classical type Lie algebras. And then you could also do other classifications using weighted Dinka diagrams and the Bala-Carter classification. Okay, so all of this is in like Humphrey's second book. Now, what I'd like to do next is I like to focus on the semi-simple theory and also the nilpotent theory. And the reason why I'm doing this is that these ideas will be important when we move to Lie superalgebras. All right, so here's a very important theorem that's used all the time. And this is called the Chevalier restriction theorem. So it says the following. So you have the torus contained inside a G. So you can actually extend that map by taking duals and say that the symmetric algebra on G maps to the symmetric algebra on T star. And when you take that restriction map and you apply invariance under G and W, the restriction map gives you an isomorphism of rings. So the first thing to notice is that because W is a finite reflection group, that means that SG star of G will be a polynomial algebra. And this theorem is quite useful because when we want to describe the center of the universal enveloping algebra, we basically use this theorem. And once we actually do that, we can describe blocks, for example, of category O using central characters. So behind the game is the Chevalier restriction theorem. So notice that this is just on the structure theory of the Lie algebra. Later on, I'll present a more souped-up version for Lie superalgebras, which is much more functorial. All right, so this sort of says what happens with semi-simple elements. And now let's talk about the nilpotent cone. So here are some standard facts about the nilpotent cone. So first of all, we know that it's a saturation of N plus under G. So for example, if you take GLN, you can always conjugate M by N matrix in terms of matrix, which is a nilpotent M by N matrix in terms of matrix, which is upper triangular, strictly upper triangulars. So basically, that's what the first statement says. And then you can actually calculate the dimension of n. It's just twice the dimension of n plus, which is actually equal to the number of roots. And with this characterization, you can actually make a map from this orbit space to n. And this is what's called the Springer resolution. And this resolution of singularities is used quite a bit in geometric representation theory. Now, I alluded to the fact that the nilpotent cone is an affine algebraic variety. And so this is the theorem which actually tells you that. So suppose you have the nilpotent cone of a complex semisimple Lie algebra. So what you can do is you can realize the nilpotent cone in terms of the zero set of G invariant polynomials without constant term. So that's what the plus means. So you look at the zero locus of all these polynomials, and that actually characterizes the nilpotent cone. And so if you want to know the coordinate algebra of the nilpotent cone, you just take S of G star, and then you factor out by the ideal generated by these polynomials. So for people who may know a lot about this theory, I mean, you also have what's called the harmonic decomposition. So it turns out that S of G star is a free S of G star G module. And you can actually write S of G star as a vector space tensor product with S of G star G with the coordinate algebra on the nilpotent cone. So there's this really tight connection between nilpotent elements and sort of the Chevrolet restriction theorem. Okay, let me ask, this is the sort of basics about Lie algebras, semisimple elements and nilpotent elements. Let me ask, are there any questions at this point before we move to Lie superalgebras? No? Okay, so let's move to Lie superalgebras. All right, so what I'll do is I'll start with the basics on Lie superalgebras. So what is a Lie superalgebra? So I'm assuming everything is finite dimensional throughout the talk. So it's basically a Z2 graded vector space, and you have a bilinear operation called the super bracket, which satisfies this skew commutativity axiom. That's sort of the first bullet. And then the super Jacobi identity. So these relations are on homogeneous elements. So the bracket A is just denotes the degree, whether it's 0 bar or it's 1 bar. Now, one thing to notice about Lie superalgebras is G0 is actually a Lie algebra. And you could take the group associated with G0, call it capital G0 bar. And G1 is a module for either the Lie algebra G0 or the algebraic group G0 bar, right? And the way that G0 bar acts is by the adjoint action. Okay, so we're gonna use this action quite a bit. So the even part, G0 bar, is gonna act on the odd part. And what we're gonna do is we're gonna look at the invariance of that when I look at the symmetric algebra on G1 star. Okay, so that's going to be kind of the setup, and we're going to try to do some of the same things that we have seen for Lie algebras with that particular action. Okay, let's move on. All right, so what is the most standard Lie superalgebra? Well, it's the Lie superalgebra GLMN. So this consists of n plus n by m plus n matrices over the complex numbers. And so what I'd like to do is show you what G0 bar is and what G1 bar is. All right, so G0 bar consists of the block diagonal matrices, with the m by m block A and the n by n block B, right? So G0 is isomorphic to GLM cross GLM, right? And if you look at G1, you sort of look at the complementary blocks. So those consist of matrices with 0, C, D, 0. Okay, so those are considered the odd elements in there. And as you can see, G0 bar is going to act on G1 just by using the adjoint representation. Okay, and what we'll do is we'll actually think of using the group adjoint representation on G1 bar, throughout the top. Now, you have to be careful a little bit with the supercommutator. So with the elementary matrices, you actually can write out the supercommutator in this way. So EIJ just represents the elementary matrix with 1 in spot IJ, right? And notice that if you're looking at the Lie algebra commutator, you don't have the -1 to the degrees up there. But because we're working with superalgebras, let me see if I can point this out. Maybe, I don't know if people can see this, but this part over here, can people see the cursor at all? Yes, no?
Yes, we see it.
Okay, good. Okay, so with this part over here, you can actually, that accounts for the superalgebra part right here. Okay, good. Now, in 1977, Katz gave a beautiful classification of simple Lie superalgebras. So this is somewhat reflective of the classifications in characteristic P for modular simple Lie algebras, which happened much later. Okay, so you have the ones which kind of are called classical, and then you have the ones of Cartan type, right? And characteristic P of these Cartan type Lie algebras, too, which are finite dimensional. But today, what I'm just going to do is I'm just going to focus on the classical ones. Now, when I mean classical, I mean that the G0 part is a connected reductive algebraic group, and G1 is completely reducible over G0 via the adjoint representation. And so what I'm doing here is I'm just listing the classical simple Lie superalgebras. So technically, these Lie superalgebras may not be simple, but a lot of times we sort of think of them as being in the class of simple Lie superalgebras, because GLMN is close to being simple, but technically it's not simple. But I'm just going to throw it into this pile because we can deal with these. All right, so technically this isn't the way the classification is stated, but I just want to sort of point this out from an organizational viewpoint. Okay, so the idea is the following. So you have these infinite families. So you have two types of infinite families. You have this infinite family up here, and these are analogs of AN, BN, CN, and DN. This OSP is kind of a hybrid between SO and SP, right? So that gives you these Lie superalgebras, okay, and they're pretty well studied. There's some exceptional ones, the D21 alpha, G3, and the F4. And then there are also these ones which are called strange and queer, I believe. And I call these outliers. Okay, so these are Lie superalgebras that really don't have an analog in terms of the classification as simple Lie algebras. And you'd like to handle them sort of in a similar way as you would for the other ones. Okay, so now what I'd like to do is I'd like to present the main questions for my talk. All right, so here's one of the first questions. So the first question is there a unified setting for the structure theory of simple classical Lie superalgebras? For example, are there natural triangular decompositions? So, with our simple Lie algebra, we know that we had a root space decomposition. All right, so what I'm going to do is I'm going to answer this question in my talk. Now, the F is not going to be an actual torus like you know a torus is. It's not going to act semi-simply. So this F is going to contain both even and odd parts. And it's going to be a really important subalgebra for us to sort of study and to introduce. Okay? So you're giving up complete reducibility by going to this F. Okay? And the next thing is, can we actually use this new Lie theory to unify the representation theory of these Lie superalgebras, and not simply study these algebras on a case-to-case basis? So, you know, if you look at the literature in this subject, you know, people tend to study like representations of GLMN, representations of OSP, representations of PN. So it's basically, you know, one algebra at a time. And the idea is we want to get away from that. We want to make it more like the structure theory for Lie algebras, where you have like Weyl groups and where you have objects which are run across all families. Okay. All right. So the first thing I need to introduce is I need to introduce this F. And the idea with this F goes back about 15 years. So it originates from work that I did with Brian Bowe and John Kujawa. It appeared in 2008, but basically started it around 2005. And the idea is the following. We are interested in cohomology of Lie superalgebras. And what we wanted to do was we wanted to find an algebra which actually detects the cohomology, right? So using the action of G0 on G1, and that, so you have to actually use some invariant theory in the game. So we're actually using some invariant theory of algebraic groups to actually construct these Lie algebras using stabilizers and semi-simple elements and so forth and so on. So there's a whole machinery out there. So we use the invariant theory and actually some geometric invariant theory to construct these algebras. So they sort of come from geometry, but you can make this very precise in terms of creating these algebras. So the first thing is if you have this type of action, what's called a stable action, then there's a subalgebra that you can make. So it has an even part and an odd part. And basically it's isomorphic to either copies of SL11 or GL11. And when you take the restriction map in cohomology, this is an isomorphism. And N here is some reductive algebraic group. Okay, it's sort of a normalizer of G0 on F. Okay. Now, you can also do this using what's called the polar action. So this goes back to work of Daydock and Katz. And you can get another subalgebra, which is isomorphic to copies of Q1, such that the restriction map in cohomology is an isomorphism. And here, WE is a finite reflection group. And surprisingly, I mean, this happens a lot. I mean, there are a few cases where the stable and polar action don't work, but generally speaking, you can actually do this for most classical Lie superalgebras. So let me put this in a bigger context. So it turns out that when you have a classical Lie superalgebra with the stable and polar action, then you can embed the E inside of the F, and the F will be contained inside the G. And then you have the following isomorphism of rings. So the horizontal arrows all represent restriction maps, okay? And notice that the top line, these are all isomorphisms. The bottom line are all isomorphisms. The bottom line should sort of, you should think about the Chevalier restriction theorem that I introduced earlier, all right? So, and the way to sort of think about this is that we've made the Chevrolet restriction theorem functorial. We've given actual functorial meaning to this restriction theorem that you may see in LieJor. Okay, and so in this case you have one more algebra. So normally you'd have just things going from G1 to maybe E with a finite reflection group, but we have this intermediate thing over here, which turns out to be quite important also. Another idea that kind of came about too is that when you look at modular representations of finite groups, you have kind of a local global principle. So you have elementary abelian subgroups, you have CELO subgroups, and so this kind of reminds you of that you can actually detect cohomology on certain subalgebras or subgroups. And so that was kind of a motivation for developing this theory. All right, so let me give you some examples. Okay, so here's what a detecting subalgebra looks like. So if you take GL3-2, then basically you have the even part looks like part of the torus, right? So you have GL3 here, and then you have GL2 down here. So you have part of the torus, but then you have to add this odd stuff too. Okay, and it sort of coincides with sort of taking the diagonal sort of on the odd part, whatever that means. Okay, so this is kind of the odd torus in some sense, and this is the even torus, or part of the even torus. So if you had like GL3-3, then you would actually have stars here, and then one more star down over here. So you can imagine for GL3-3 what a detecting subalgebra would actually look like. Now, if you want to get the E, all you have to do is you just equate the entry here in this corner and then down here. And then you equate this entry here and that entry there. And that actually gives you a subalgebra of the F. Since we're not working with the E so much in this talk, I'm not going to focus on that. I'm going to focus more on the subalgebra F. All right. Now, since we have a functorial description, we actually came up with a conjecture. So I need to explain parts of this conjecture to you. So if you know something about the cohomology of finite groups or finite group schemes, you have the whole idea of support varieties. So how do support varieties kind of originate? Well, you take the cohomology ring, and what you want to know is whether the cohomology ring is finitely generated. So I'm just going to focus on this bottom part down here first. So here's the cohomology ring. Now, by the previous theorem, this is a ring of invariants, and it's invariant under the action of a reductive algebraic group. So because the symmetric algebra is finitely generated and G0 bar is reductive, that means the cohomology is also a finitely generated algebra. In fact, most of the time, it's just a polynomial algebra. Now, this algebra, GG0, acts on this cohomology ring. And you could prove that this cohomology of MM is finitely generated over this cohomology ring. So that means you could just look at the support of that, and that gives you the support variety. So you look at all prime ideals such that when you localize, you don't get zero. And this gives you the support variety of the module. Okay. So this is a standard definition of support varieties. And you can do this for E and F. And the point is that we want to compare the support varieties over G, F, and E. And it turns out that when you have these actions, you can actually do that. So it's not hard to actually show that these maps are actually injections. So this thing I'm circling is actually an injection. The hard part is to actually show that the map are surjections. And so we conjectured that the support varieties for G, F, and E should all be the same or isomorphic. And the advantage with this is that we don't know very much about the cohomology for G or the support varieties for G, but for E, you can actually write what's called a rank variety description out. So you can make it very, very concrete. So if this conjecture is true, then you can get a very concrete realization of the supports for these GG zeros. Okay. All right, so we define detecting subalgebras. With detecting subalgebras, we have like a Chevrolet restriction theorem, and then we can use that to create support varieties. And so what is this all good for? Well, many of you know that atypicality is a word used in Lie superalgebras. So here's the definition that Katz and Wakimoto gave for the atypicality of a weight, lambda. So it's just a combinatorial description. So I could just read it to you, or basically if you have a basic classical Lie superalgebra, you have some type of non-degenerate form. Now it has a bunch of adjectives along with that, but I'm not going to say what the adjectives are. And the idea is that with this non-degenerate form, you can actually look at the maximal number of linearly independent, mutually orthogonal isotropic odd roots for which lambda plus rho. So rho is sort of the analog of the half sum of positive roots in this case. And you just want lambda plus rho alpha to be zero. So this is just a purely combinatorial definition of a numerical invariant called the atypicality. And people have actually come up with combinatorial algorithms to compute the atypicality of a weight. Okay, so there are various tricks that you can do and rules that you can do to compute the atypicality. All right, so the striking thing that we proved was the following. So let's say you take a finite dimensional irreducible representation, then the support variety dimension is equal to the atypicality for any basic classical Lie superalgebra. So for GLMN, this was done by Bo, Kujawa, and myself. And for OSP, this was done by Kujawa. And for the exceptional types, you can actually sort of do this by hand. Okay. Now, I don't know if for people in the US, they know that you know, there are people out there, maybe people on the extreme right and on the extreme left politically, who want a revolution, a political revolution. So, so what people have been doing is they've been defining this atypicality in a very combinatorial way. So I want to actually declare a revolution at this point. Okay, so I don't know if this talk is recorded. Maybe this will go down in history. Who knows? Okay, so here's what I want to say. All right, so I'm going to give you a new definition. So the new definition of atypicality is just going to be the dimension of the support variety. And what's the advantage of this? Well, the advantage is that this holds for any module. You just don't need an irreducible representation. So you could just look at the atypicality. It sort of measures how sort of difficult the module is to study, right? And you have a geometric interpretation of this, right? And so for type QN, for example, there are various definitions of atypicality. We still don't know which one is the right one. But my point of view is like, who cares? Now we have a new definition which holds for everything. So I'm sort of declaring this as the new definition of atypicality. We'll see if it sticks or not. All right. I have to give you the full picture, so, okay, good.
Okay, continue.
All right, great. So now I'm just going to move on. All right, so we talked about semi-simple elements. All right, so the next thing you should ask is, what about nilpotent elements? Oops. Okay. So what about nilpotent elements? Well, we just define nilpotent elements the same way that we define nilpotent elements for complex semisimple Lie algebras. So we have the action of G0 on G1 star, and we can ask for the G0 invariant polynomials without constant term. And we can look at the zero set of that. Okay, very natural definition. This isn't really our definition. This is motivated by Victor Katz when he defined nil varieties for general graded Lie superalgebras. Okay. All right, so what's the natural theorem to prove? So this is a theorem that is fairly recent, and it was proved by my student Andy Jenkins and myself. And it says basically the following. So if you look at script n, it has finitely many G0 orbits. Okay, just like the nilpotent cone for simple Lie algebras. Okay. Now, what are the things that we did in this process? So we actually have a complete classification of orbits for GLMN. Right? And if you look at the famous Duflo-Serganova self-commuting variety, we actually proved that their variety is contained inside this nilpotent cone. This is for all classical simple Lie superalgebras. And Duflo-Serganova actually proved that X has finitely many G0 orbits for basic classical Lie superalgebras. So since we have this inclusion, we get the result, and we actually generalize the result to all classical simple Lie superalgebras. Let me say something further. So this script X is used quite a bit in their work. I mean, they construct what's called the Duflo-Serganova functor. And what we sort of believe is that we believe that the N has a richer theory, that maybe that N is the right variety to study if you want to actually do more with like geometric representation theory. Okay, so this N here sort of comes from the setup with the detecting subalgebra very naturally. So it sort of fits into this game. Okay. All right, so now I need to actually present another piece of the puzzle. So we had the detecting subalgebras, we had G, we also had this conjecture that I mentioned. And so what we need is, we need an algebra which is sort of a bridge between the detecting subalgebra and also the Lie superalgebra itself. So we discovered these algebras about 2 years ago. So these are called BBW parabolic subalgebras, right? And I'll say what's special about these. So this was developed by Dmitry Grantcharov, who's here, I guess, and Nikolai Grantcharov, myself and Jerry Wu. Nikolai and Jerry were undergraduates at UC Berkeley during this time. We wrote the paper, we did much of the paper at MSRI. They are in the class of 2019 graduates of UC Berkeley. So interestingly enough, our project started in 2018, and my daughter was also an undergraduate at Berkeley at the time, and she actually introduced me to Jerry, who was a math major. So there are all these circumstances that happened that actually led to this paper. So what we did was we answered the first question. So if I have a classical Lie superalgebra over C and F is a detecting subalgebra, then there's a parabolic subalgebra, i.e. you have a sort of root space decomposition which complements Weyl. And so you have this kind of root space decomposition, but then you have this F in the center, okay? And F is not, it's sort of like a levy, but it's more complicated than a levy in some ways. So you have to give something up to study Lie superalgebras, and this is the part you kind of give up. And for now, I'm going to call the parabolic B a BBW parabolic subalgebra. Okay, so this is kind of abstract. Let me just give you what these things look like. So again, this F is a detecting subalgebra. So you have sort of the torus part here and the torus part here. And then in the odd part, you have sort of diagonal entries here and diagonal entries there. Okay, so that gives you the subalgebra F. And what we can do is we sort of do for GLMN, it's easy, right? You just do what's very natural. You sort of complement this by just taking sort of the upper triangular blocks in each of the 4 matrices involved. All right. So you can imagine what the picture looks like for GLMN, and it turns out that it actually works for OSP. This also works for type Q, because all you need to do is match these 2 blocks and these 2 blocks. And then you can also show this for D21 alpha, F4, and G3 also. Okay, so this gives you an example of BBW parabolic. Now, with the BBW parabolic, we can sort of do things, make constructions that you would normally try to do for algebraic groups. So it turns out that you can find an algebraic supergroup. I should be careful, it's supergroup scheme. Okay, so you have to work with supergroup schemes here, which are sort of like supergroups, but you technically have to be a little bit careful. And such that when you take its Lie algebra, you just get script G, right? And for the BBW parabolic, you can also find a parabolic subgroup scheme. And the nice thing about this setup is when you look at the category of rational G modules, like you would for algebraic groups, it's equivalent to modules for G, which are completely reducible over the even part. All right, let's move on. All right, so now what you do is you just create the induction functor. So this functor is just like you would do for, you find in like Janssen's algebraic groups book, right? So you take a rational B module and you look at the induction functor from B to G. And what's interesting is to kind of understand the higher right derived functors of induction. And then what you do is you kind of create this Poincare polynomial. So you look at the dimension of these cohomology groups, and for now we just want to work in the case when M is the trivial module. And then you sort of grade these by using the degrees over here. Now, you know, with algebraic groups, reductive algebraic groups, we know by Kemp's vanishing theorem, Hn induction from B to G of C would actually be 0 if G and B were reductive algebraic groups. But it turns out when we have these supergroup schemes, we could have higher cohomologies which do not vanish. So in this super case, Kemp's vanishing theorem, and we'll see examples of this, does not hold. Okay, but yet we could still do some computations. All right. All right, now you have these cohomology rings that I introduced before. So you have the relative cohomology ring, and then you have the relative cohomology ring for B. And then you can create similarly Poincare polynomials for this. Okay, and so here's sort of the big theorem. So it turns out that as long as you don't have Pn, then there's a BBW parabolic such that the following is true. So you can actually decompose the cohomology for B as a cohomology for G tensored with the group algebra on a finite reflection group. And the grading of the group algebra is sort of given by the Poincare polynomial. And so, of the finite reflection group. And so I say this again because the BBW parabolic subalgebra, we sort of define it as having this property. So you have these Poincare polynomials here, and these Poincare polynomials come from cohomology. But the amazing thing is they turn out to be equal to a Poincare polynomial, which comes from a finite reflection group. So basically, you're sort of looking at the elements of having a certain length. which give you the Poincare polynomial. So this gives you sort of a connection between W1 and also the cohomology over here. And you just have to insert a power of t depending on what superalgebra you have. So for Qn, you have to insert s equals t. For GLMN, you have to insert s equals t squared. Okay. All right, so where does this finite reflection group come from? It actually comes from a subgroup of the Weyl group for the 0 part. Okay, so I'll kind of move on from there. And in the GLNN case, the W1 part just comes as the diagonal embedding in terms of sigma n cross sigma n. Okay, so there's a very nice picture here. Now, what are the ingredients that actually go into some of this work? Well, one of the ingredients involves using this sheaf cohomology, and the idea is that, and this idea comes from work of John Brundon, is that if you want to study the sheaf cohomology for the supergroup scheme over here, you know that this is going to be completely reducible over G0. So I can actually restrict my action down to G0, and you can replace this by just looking at the even part under certain assumptions. And what you have to do is you have to replace M by M tensor this exterior algebra over here. All right. So you can actually transfer the problem from the supergroup down to algebraic groups by using this theorem. And something else I want to point out is that by doing so, you can kind of see what's going on, because right here, you're going to try to use the Borel-Weyl theorem, right? For G0, G0 is a reductive algebraic group, but these are going to be things which involve odd roots. So you have this intermixing between the even theory and the odd theory, which is kind of given by this theorem over here. And we actually work all this out. So that's why we're able to do what we can do. Okay. Now, another thing that happens is this induction is very functorial. So you can actually create a first quadrant spectral sequence by just composing the Hom functor with the induction and use the Grothian deconstruction to get this. So this turns out to be quite important because we could relate the higher cohomologies here and the X in the GG0 category and also the BB0 category. So what is the byproduct of all this? Well, the byproduct is the proof of the conjecture. I should remark, I don't know if people have done this before, but I actually found out how to put the emoji in using text. So that was one of my accomplishments during this talk. All right, so you can use the spectral sequence to actually relate the cohomology with trivial coefficients to the cohomology for just arbitrary M. So you have actually one spectral sequence acting on another. And by studying that and using these BBW parabolics, what we do is we actually show that the cohomology, when I put in trivial coefficients into the spectral sequence, actually collapses. And by showing it collapses, it allows you to show that this map down here is actually a surjection. Okay. So that we knew there were injections before, but we can actually show it's surjective by using this spectral sequence setup. So let me also mention that I said that that theorem holds for all classical superalgebras except for Pn. So for Pn, for n bigger than or equal to 4, we have to use the results of LieJor, Nakano, and Zhang who actually proved this conjecture for type 1 Lie superalgebras. So this was actually known back in 2010 for type 1 Lie superalgebras, but it wasn't known in general. So for type PN, we could actually appeal to that result. So now we can cover all the simple classical Lie superalgebras and say that the isomorphism on support varieties it holds. Okay, so in the last couple minutes, I just want to talk about a few new directions that we're looking at. So with Chunju Lai, Arik Wilbert, and myself, we've actually developed a category O theory. So you have a triangular decomposition. You know, natural thing to do is try to figure out category O. You know, what are possible causationalistic theories? You know, cohomology. We find this is a very interesting setup because, you know, if we can actually find some way to prove something about the X groups over here, maybe all the other causationalistic theories would actually fall that have been proved before for Lie superalgebras. Now, one thing to notice is that this is a standard result. So if you have a Verma module here and you have a simple module, then it turns out that the X is really a souped up version of Costin's theorem. So for finite dimensional representations, Costin theorem for Lie algebras, you know, gives you this result as a T module, for example. All right. Now, here we don't have a torus, but we have this detecting subalgebra, so we have to soup it up a little bit. So basically, we're looking at the number of times that this irreducible appears in the socle of this module. And that's what actually gives you the X. Okay, so this is kind of a souped up version of Costin's theorem. And of course, L mu could be an infinite dimensional module. All right. We don't know the answer to this, but we're working hard in terms of trying to understand this. And my student, David Galvin, actually has results for these detecting subalgebras and these BBW parabolics. And so the natural question to ask is, what's the cohomology of n plus with trivial coefficients? And it turns out to be more complicated than you would think. And so for n equals 1 and 2, he's actually done the computations. For n equals 1, it turns out that the weights are sort of similar to Costin's theorem. But for n equals 2, it gets pretty complicated. But he's actually finished the computation for n equals 2. Okay, so I'm nearing the end of my talk. I promised people that I would actually put something up involving Lee Jordan. And so this was a picture from the first conference, I believe. Okay, so thank you again for your attention.
Thank you very much. Okay, now questions, comments, please.
Hello, may I ask a question?
Sure.
Of course.
You know, you mentioned B double parabolic. What's the difference between usual super parabolic and this one?
Well, this is just a very special type of parabolic. There are lots of ways to, I mean, you can ask Dimitar, he's more of an expert on this, but there are various ways that you can actually create parabolics. This is just a very special parabolic. And it's a parabolic which is compatible with the detecting subalgebra.
So it means it's subset of usual parabolic, no, like stabilizer of Flag varieties.
I believe that is,
Super varieties.
yeah, you could sort of define it in terms of hyperplanes.
Yeah, Flag super varieties.
Yeah.
Okay.
I think it does have an interpretation that way. Yeah.
Mm-hmm.
Okay, more questions, please. Comments, questions? Usually the questions appear a little later after some informal talk, like some informal discussion after the talk maybe. Okay, thank you very much. Let us thank Grantcharov again. While people are thinking about probable questions, I will announce for the next Thursday. The next Thursday we will have as our speaker at our seminar Claude Sibils from Montpellier University, and he will speak on controlling the global dimension. It's announcement for the next Thursday, but well, still, if anybody has questions, comments, yes, wait a little.
I could stay around, so. Oh, yes.
Thank you, everybody, for participation. Thank you, Dan, again.
Oh, yeah. My wife would like to say hi.
So, see everybody for the next.
Yeah, okay. Hi, you know you want. Yeah. Okay.
See you, all of you, for, well, the next Thursday.
Yeah.
Till the next Thursday. Bye-bye.
Okay. Thank you again.